Good morning everybody, hope you're all healthy and safe. Let us continue learning the properties of self-adjoint operators. So till in the previous lectures and all, we were discussing about the properties of our self-adjoint operators. We have discussed a few. Now in this lecture we shall begin with the property 6.1.6. This is a pretty much easy property which I leave it to you guys to just verify it. You can just refer your textbook for the proof also. It is a simple proof, that is the inner product A of x comma x is an element of R, that is it is a real number if and only if A is symmetric or A is self-adjoint. Okay, so that is the inner, if the property, the operator that we are considering is symmetric, then the inner product A of x comma x is a real number, it is not a complex number. So just try to work out the proof of this property. It is simple, you can just work it out. So let's move on to the next property, and this is the last one. This property 6.1.7. The property is as follows: let A be a symmetric operator, and we are defining norm of A is equal to mu, which is supremum of modulus inner product AXX for all x whose norm is 1. Okay, this is how we are defining the set. That is, norm of A is equal to supremum of modulus inner product AXX where norm x is 1. Okay, and we are just denoting it by mu. Then the property is at least one of mu or minus mu are elements of sigma of A. Okay, that is, if we are considering an symmetric operator and if we are allowing the norm to be of this form, then that norm, either the positive or negative value of that norm will be a element of the spectrum of that operator. Okay, that is what the property states. So we have to show that either mu or minus mu is an element of the spectrum. So let's move on to the proof of this property. So first of all, I'm going to choose an xn with norm of xn equal to 1. Okay, if norm of xn is 1, then what was mu? Mu was supremum of mod inner product AXX. Okay, the condition was norm x should be equal to 1, right? So I'm choosing xn such that norm xn is 1. So not that as norm xn is 1 means I can say that modulus inner product AXN xn, that is a particular term of this sequence or this collection, this will be less than or equal to mu, right? Now in the previous property, that is in property 6.1.5 that we had done in the previous lecture, we had defined a term called C. C is equal to nothing but supremum mod inner product AXX by norm x square, right? So here norm x, if I am just replacing, instead of x I am considering xn, I will get supremum inner product, or just consider the term modulus inner product AXN xn divided by norm xn means divided by 1, so that doesn't affect the term. Now if in this proposition we had C was of this form, and as A is symmetric, here we are considering symmetric operator, right? So as A is symmetric or self-adjoint, we have C is equal to norm of A, right? And by definition, what was norm of A? Norm of A was nothing but mu. That is how we had defined in the theorem. So as modulus A of xn xn inner product AXN xn is less than or equal to mu, I can conclude that if I am considering it as a sequence, I can say that inner product A of xn xn modulus will tend to mu. Okay, that is modulus of inner product AXN XN tends to mu. Now suppose inner product AXN XN converges to point lambda. Okay, then what can I say? If this is converging to lambda, the modulus of this term is converging to mu, right? That is what we have got right now. So this lambda can be, it is actually modulus of mu, so it can be either lambda is equal to either plus mu or lambda is minus mu. I hope it is clear. We have obtained that modulus inner product AXN XN tends to mu, and if we are supposing that inner product AXN XN tends to lambda, then lambda should be either plus mu or it should be minus mu, right? Now next, what are we going to show? We shall show that lambda is an element of the spectrum of A. This is what we are going to prove. So let's see how we are going to do that. Now consider norm of AXN minus lambda XN square. Okay, right? So this is inner product AXN minus lambda XN comma AXN minus lambda XN. So I am simplifying this. After simplification, I get this is equal to norm of AXN square plus lambda square into norm of XN square minus 2 times lambda into inner product AXN XN. Okay, after simplification you can just verify it if you want to. Just open it up using the property of inner product and you will get this result. Okay, so what is norm of XN square? That is 1, and this norm of AXN square, I can write this as this is less than or equal to norm of A square into norm of XN square, right? So this will be lambda square into 1 minus 2 times lambda into inner product AXN XN. Now norm of A was nothing but mu square. Okay, let me see. Norm of A was nothing but mu, not mu square, sorry. Norm of A is equal to mu. So this implies norm of A square will be equal to mu square, right? Mu square will be same as lambda square, because lambda is either plus mu or minus mu. Anyway, lambda square will be mu square itself. So I can write this as lambda square, again XN square is 1, so lambda square plus 1 more lambda square, that is 2 lambda square minus 2 lambda into inner product AXN XN. Now we have seen, or we have supposed that AXN XN tends to lambda. So as n tends to infinity, this term tends to lambda, so I get 2 lambda square minus 2 lambda square, that is 0, right? So I get norm of AXN minus lambda XN square will be less than or equal to 0, right? Or it tends to 0, it is less than or equal to 0. So, but we know the norm is always greater than 0. 0 is less than equal to norm AXN minus lambda XN square, right? So combining these two inequalities, what can I say? I can say that norm of AXN minus lambda XN square is equal to 0, or norm of AXN minus lambda XN is equal to 0, and this implies A of XN minus lambda of XN equal to 0, and this implies A of XN is equal to lambda of XN. This is true for every XN, its norm is 1. So this implies lambda is an element of the spectrum of sigma of A, right? So if lambda is an element of sigma of A, I can say that either plus mu or minus mu is an element of the spectrum of A. right? So that was the proof of this theorem. We just had to consider the property that we have done before, and we just had to verify it. So remember property 6.1.5, and with the help of that we have proved that if the operator is symmetric, and if we are defining norm to be a norm of that operator to be of this form, then at least minus of that norm or plus of that norm will be an element of the corresponding spectrum. So that's it. Thank you.